Well, thank you very much. It's a real honor to speak here. And I have to say, many people in the longevity research community, when my book came out, probably wondered, who on earth is this guy? And I seem to have gone from zero to expert in the course of one book, which sounds like a Tesla ad when Teslas used to be fashionable. But anyway, this is a book, and I'm going to summarize, and by the way, it's coming out in Italian later this year, and I'm going to summarize some thoughts from the book. Now, I'm not actually as remote from the longevity field as you might think, because long after the structure of the ribosome was solved, the field has moved on to initiation and regulation of translation, and these are processes which are central to aging. For example, the target of the TOR pathway or the integrated stress response directly have to do with things that we study in our lab, but we don't study aging per se. And I came to the book with no bias or no vested interest, and part of my motivation was the extraordinary amount of hype in the aging field, and I thought it'd be good for somebody with no particular skin in the game, but close enough to the field to write about it. So I'm going to talk about a few issues, and some of the people in the community may feel like this is a bit like being forced to take a cold shower, but actually, you know, there'll be other speakers here who will warm you up and give you fluffy, warm towels, so it'll be okay. So anyway, here we go. So the first question is aging programmed? And that is a big source of confusion because most molecular biologists, including me, don't actually think about evolution. And the fact is, if you talk to evolutionary biologists, there's almost universal agreement that aging is not programmed. So then how do you explain that species have such different lifespans? You can have an insect that lives for a day, and you have other species that live for several hundred years. I like to joke that there's a Galapagos tortoise walking around now that might have encountered Darwin one day, you know, when he was alive. So how do you explain that? Well, take a look at this graph. In most classes of animals, including mammals, longevity is roughly correlated with size. It's actually more correlated with metabolism, but because metabolism is highly correlated with size, you get this graph. And you know, you can see we're outliers. We actually do much better than would be expected for our size. So why is this? Well, it turns out that evolution doesn't actually care how long you live. It selects for genes, and genes are basically a survival process. The selection is a survival process. So it selects for the likelihood that you will pass on offspring efficiently. And any traits that help you do that will be selected for, and others will be selected against. And so you can see how, and if an animal has limited resources, and through most of our own history we had limited resources, you have a choice. Do you put them into maintenance and repair and maintain a long lifespan, or do you put those same resources into rapid growth and maturation and production of offspring? Now, in the case of a mouse, there's no point in selecting for traits that give you lots of maintenance and repair, because long before that, the mouse will be killed off by a predator or die of starvation. And so in the case of the mouse, the species has evolved so that it grows very rapidly and reproduces rapidly, and it doesn't have a very long lifespan. So the upshot is evolution will select for traits that are advantageous in early life, even if they're detrimental in old age, because it doesn't care what happens to you after you've passed on your genes. And this has some interesting things. For example, the IGF-1 pathway, many of the caloric restriction pathways, they're essential for growth and maturation, but yet they cause us problems later in life. Loss of telomerase in somatic cells is almost certainly a cancer prevention mechanism, and yet it causes us problems in old age. And of course, there's animals which appear not to age at all. These are sort of called biologically immortal, but actually they do age, only more slowly. And the reason they age slowly is they're filled with stem cells that regenerate tissue throughout their body, and so they don't have the problem of degeneration. Now, so if aging is not programmed, what do we mean? We have genes that can affect aging and so on. Well, the point is, it's different from development. In development, genes are actually selected for a specific purpose. In aging, genes are selected for something else, like growth, like maturation, like prevention of early cancer. And aging is an unintended consequence. It's not selected against. That's the main thing. So it may have the illusion of being programmed, but it isn't actually programmed in the sense, early mortality or premature, short lifespan is not what is being selected for. Now, can we exceed our natural lifespan? Well, there's no physical or chemical law that says we can't exceed our natural lifespan. Of course, we may end up being very different kinds of animals if we do all of the things that are required to extend our lifespan. Jay Olshansky has a very funny cartoon of all the things you'd have to change in a human body to get it to live for a very long time. Now, the reality is, given this way our species has evolved, we do have a natural lifespan, even though theoretically it may be possible to exceed it, but theoretically it's also possible to settle other galaxies and colonize Mars and so on. Okay, so what is the natural limit? Well, this person is a record holder. By record holder, I mean for which there are reasonably accurate records. Jeanne Calment died at the age of 122 in 1997. You can see, as from this picture, she had a cigarette and a glass of port every day after lunch, well into her hundreds. It's not something any of us would recommend as a recipe for longevity. But she also had 2.5 pounds, a kilo of chocolate a week, which I could get behind. Now, nobody else has lived past 120, even in the 30 years that have elapsed since Jeanne Calment died. And the fact is, the number of centenarians has been growing steadily over the last few decades. But Tom Pearls told me, who runs the New England Centenarian Study, told me that the number of people living past 110 is actually not growing much or at all. And this suggests that beyond 110 or so, we're hitting some natural limit of our species. Now, another issue is defining aging. I was at the symposium in Milan yesterday and the day before, and of course, there are many definitions at that conference alone. And the definition that I like, perhaps because I'm a molecular biologist, is that it's the accumulation of changes and damage that leads to increased dysfunction or loss of function over time. And notice I say changes and damage. It's not just all damage. Some of it is like DNA methylation, for example. You wouldn't call it a damage, but it is a kind of change that may lead to aging. And perhaps the best way to leave that is to say, okay, we can't precisely define it, but I know it when I see it, which was Justice Potter Stewart's comment on how to define obscenity. So then we come to hallmarks of aging. Now, if you look at the field, almost everybody in the field relies on this idea of hallmarks of aging. They want some kind of processes to say, okay, these are involved in aging. Now, this is a very influential paper published in 2013. And it's the same authors published a follow-up paper 10 years later in 2023. The number of hallmarks has expanded from 9 to 13. In fact, their title says an expanding universe. Notice they cover almost everything from DNA damage to telomeres, to chromosome stability and methylation, protein production, nutrient sensing pathways like TOR and IGF-1, mitochondria, cellular senescence. Now, these pathways, first of all, are not independent. They're highly interconnected. And secondly, they encompass almost all of biology. So no wonder I was in a field adjacent to aging. I could have been working on anything, and it would be adjacent to aging. So the question is, are these hallmarks useful? Well, the original hallmarks, I strongly suspect, were written because there was a very influential paper called Hallmarks of Cancer, published by Hanahan and Bob Weinberg. And it was published first in 2000, and there was a revised version in 2011, also in Cell. And this was hugely influential in the cancer field. But of course, cancer is a defined disease. You know, there are diagnostics for cancer. You can say this person has pancreatic cancer, this person doesn't. So it's very different from aging, which is a multifactorial disease and is a continuum. And as I say, aging may also be related to almost all cellular processes. Nevertheless, I can see from the community that it is a useful framework, and people often work on one or the other of these hallmarks. Now, why are we all here? We've heard lots of talks about this, including the introduction, so I'm not going to belabor the point. The fact is, the combination of increased longevity and lower fertility means an aging population. This is creating a real problem for societies. And you've seen variations of this. This is in the UK, and this is before including the loss of fertility in the statistics. You can see in 1966, far more young people, very, very few old people, and in 2066 it's projected to be much fatter at the top. In Italy, it's actually almost an inverted pyramid. It's actually starts narrow and widens until it's about 50, and these people are all going to get older. So you can see there's a serious issue. And this huge explosion, this social issue has resulted in a huge explosion in longevity research. And it's led to both real advances and quite a lot of dubious claims, I have to say. And there have been some of the advances. There are more than 300,000 papers in the last 10 years. So if I applied my field as a criterion, you can assume that at least a few thousand of these papers are actually true. And and they're not published in just the three major journals. There's a whole proliferation of journals devoted exclusively to aging or longevity. Now, of course, along with that, there's a huge number of startups. There's 700 startups with many billions invested. I'm afraid I couldn't fit 700 companies here, so if your company is not on this slide, my apologies. But anyway, what this is doing also is the amount of money in the field, a lot of it from private actors, many from tech billionaires, has the ability to distort priorities in the field. And so we need to be careful about that. And of course, this is provided to me by Tom Check, who's written a very nice book on RNA, a popular book called The Catalyst. And of course, you can lengthen your telomeres. If you go to Amazon.com, there's lots of things you can buy to lengthen your telomeres. No FDA approval is required for food supplements. There are no clinical trials. Many of these things apply to many other things recommended for longevity. Now, another question is aging a disease? Okay, longevity researchers would love to treat aging as a disease. And the reason is that it's much easier to do clinical trials if you have a disease target, and you can get approval and so on. And but of course, the WHO and most of the time, mostly the FDA has not agreed that aging is a disease. Now, I'll give you both views. The view that it's a disease is based on the idea that if you look at the diseases of old age, I mean, the four major ones are heart disease, diabetes, cancer, and dementia. All of those are very, very highly correlated with age. In fact, age can be thought of as a major risk factor for these diseases. And so the view is that, well, maybe aging is the disease and the underlying disease, and these things are manifestations of aging. But the reality is, young people get cancer, young people can also get diabetes, you can have early dementia. So, it's not entirely analogous. And unlike a disease, aging is both ubiquitous and inevitable. And I feel that maybe the longevity research community should stop thinking of aging as a disease, but think of it as a process. You don't like the process, you want to do something about it. There are ways that you ought to be able to do to develop therapies or interventions without calling it a disease, where you have a diagnostic, you have this disease, you don't. Okay, now, speaking of therapies, there is a much higher bar for anti-aging therapeutics. Now, if you're a cancer patient, somebody tells you you have 6 months to live, you will be willing to take a horrible cocktail of cytotoxic drugs, radiation therapy, nasty surgery. You'll do all that because the alternative is that you're going to die in 6 months. Now, with aging, it's different. You're asking somebody to take a pill for 10 or 20 years on the promise that at the end they'll live another 10 years of a healthy life. And so the bar is higher. The bar for safety, for side effects, for efficacy is much higher for anti-aging therapeutics. Then there's the difficulty of clinical trials. Now, if you did the conventional clinical trial, you would use mortality. That's the only real test, is it working or not? And that's going to be not very financially possible. You have to wait 20 years or 30 years for a clinical trial. And of course, as business people have often said, you can't improve what you can't measure. And so there is a need for agreement. They need to have proper criteria for biological clocks or markers of aging. And there's quite a lot of disagreement. People tend to like their own clock. The methylation people, DNA methylation people like their clock. The protein glycosylation people like theirs. And the proteomics people like theirs. So what you have to do is really what the community needs to do is come together and agree on a panel and say, okay, these are all the criteria that we're going to use. Each criterion will measure something that's slightly different. At the Milan, we heard how a telomere clock doesn't actually correlate very well with the epigenetic, the DNA methylation clock. And so we have to come to some agreement on this. And finally, I want to say, even by their own criteria, by the criteria of these markers, biological age is not a single number. Within a person, different organs have different ages. So the idea that, oh, you can take this test and this is your biological age doesn't seem like it makes much sense to me, okay? So what are some promising approaches? I've talked about a number of these issues. Well, there are many promising approaches. I'll tell you the ones that I particularly think are promising. Among them are drugs that mimic caloric restriction, because it's been shown that if you take animals from, whether they're worms, flies, or mice, or even monkeys, you can calorically restrict them, and the calorically restricted monkeys will be healthier and resemble younger animals. Now, one caveat, Leonard Hayflick, a father of this field, who first showed the business of cellular senescence, pointed out that the control animals were all animals that were fed an extraordinarily rich all-you-can-eat diet. This would be like comparing a guy who's at some Midwestern buffet, gorging himself, with somebody from, say, Northern California who's on this vegan diet, okay? And they're not comparable. And so the question is it restricting calories, or is it just having an all-you-can-eat diet that's bad for you? It doesn't matter. What matters is the number of calories you consume does seem to matter, okay, whatever the relative comparison is. And many of the drugs that affect various caloric restriction pathways mimic some of the effects of caloric restriction in the sense of producing effects on older animals that mimic the effect of caloric restriction. And my book doesn't talk about GLP-1 agonists, but that's the latest in this class. Now, I should point out, all of these have some problems, okay? For example, rapamycin is an immunosuppressive drug. It's given for organ transplant recipients. GLP-1 agonists, like the others, cause muscle loss, and frailty is a real problem as we age. And so the question is, how useful are they going to be? They may reduce markers of aging. How useful are they going to be when taken in healthy people over a prolonged period? If I were a graft recipient, of course I would take rapamycin, whatever dose doctors would recommend. So this sort of thing requires careful clinical trials, and that needs to happen before I think they're ready for prime time. But it hasn't stopped, many people in the longevity field taking them anyway. Now, targeting senescent cells, the senescent cells serve an important purpose. For example, when cells get damaged or stressed, they can go into a pathway that triggers senescence, which is a state when they can no longer divide, they're no longer properly functional, secrete inflammatory compounds. But as we get older, the number of senescent cells we accumulate becomes larger, our ability to clear them declines, and we get systemic inflammation, which causes organ damage and creates more senescent cells. And so targeting senescent cells for destruction has been another useful avenue. The question is, can we do this safely? Can we do, you can't kill off all senescent cells, but can we kill them off in sufficient numbers so that it's safe and it doesn't have side effects, it doesn't kill healthy cells, etc. Now, some years ago, I think a couple of decades ago, it's actually a much older experiment. A couple of decades ago, scientists at Stanford showed that if you connected an old animal with a young animal, the young animal suffered from the old blood, and the old animal benefited from the young blood during this transfusion. And this resulted in a number of companies, typically in California, I should add, sprouting up to extract blood from young donors and selling them at a huge markup to billionaires who wanted transfusions. And of course, one of the tech billionaires decided to start his own company, as it were. He got transfusions from his son. This is Brian Johnson in the middle. Got transfusions from his son on the right, and then gave blood to his father on the left. And now this is a guy who spends $2 million a year on longevity, on his own longevity. He considers himself a sort of N=1 pioneer of longevity experiments. But even he decided that it wasn't actually doing much, and I think he stopped doing the transplants. But it doesn't mean that this can't be a subject for research, because we do know factors in blood change, and maybe some of the factors are detrimental in old age. We need to identify them, see what they do, what is their biology, and can we use them for intervention, either by inhibiting them or doing something else. Another one is metabolite loss and supplementation. And the idea is that as we get older, our ability to make important metabolites declines. And maybe these can be restored by supplementation of micronutrients. And one of the fathers of this field was Bruce Ames, who's very famous for the Ames test. Many of you who work on biology of cancer know that the Ames test is what everybody uses for test of carcinogenesis for new compounds. Well, later in life, he became interested, not surprisingly, in longevity. And he started working on things that might improve mitochondrial health in old age, and came up with this idea of acetylcarnitine and lipoic acid, which, by the way, I've noticed has found its way into all these vitamins which are sold for older people. If you look like over 70s vitamins, you'll find that it's got acetylcarnitine and lipoic acid. So somebody there is reading the literature in these companies. And Ames himself died last year at the age of 96, so something clearly worked for him. So anyway, he didn't stop with those two compounds. He kept trying various other things. And 20 years later, he published a big list, and the list kept expanding. So now, a large number of micronutrients or vitamins are part of his list, okay? So it almost seems like almost everything you make might be useful, because our ability to make them decline. And of course, the big rage in the longevity field are these NAD precursors. Now, NAD can't be consumed by itself for various reasons, absorption and stability and so on. But two precursors of NAD, NMN and NR, are well tolerated, can be absorbed and used to make NAD in the cell. And they can restore your NAD levels to sort of levels that you had when you were younger. And animals, they've shown to slow down the loss of stem cells or muscle degeneration, but interestingly, not lifespan. And it's widely marketed. And when I wrote the book, which was two or 3 years ago, it was $300 million a year. It's expected to be over $1 billion a year by 2028, but I bet it's going to exceed that even faster. And finally, we come to an exciting area, which is going to be the subject of at least two subsequent talks, one by the person who really founded this field. And that is, as we grow from a single cell to a final animal, our cells differentiate and finally differentiate into the final tissues. And the cells that are responsible for making these are called stem cells. You'll hear a lot more about them. I'm only going to say that normally this process is one way. And the question is, can we make it go backwards the other way? And that could be a very promising approach to aging, but of course, there are all sorts of issues of long-term safety, of delivery, of dosage, all of those things which the community has to address, and you'll hear more about them later. Now, the whole field, and we've heard many introductory talks say, it's not about living longer, it's about living healthier, improving health span. And this idea comes from a 1980 paper by James Fries called Aging, Natural Death, and the Compression of Morbidity. That's the term, compression of morbidity, that he applied, and it's been used in the field. And what he meant was what he wanted to compress is the years of unhealthy life. He wants to compress that to as short a life as possible. And I heard Rick Klausner at the opening of Altos Labs in Cambridge say they were not interested in extending lifespan either. The goal is to die young after a long time. And of course, I thought even at the time, if you're young, why would you suddenly die? Everything's working fine, you're going to collapse suddenly. Well, the point is, even James Fries, when he wrote the paper, said that the idea was a little bit like the one-horse open shay. Now, a shay is a one-horse carriage, which was popular in the 19th century. And the idea was that there was this wonderful one-horse shay, which Oliver Wendell Holmes describes, which was constructed so perfectly that all its parts wore out at exactly the same rate. And so the farmer was riding along happily, the shay was working fine, and 1 second later, he found himself on the ground, surrounded by a heap of debris, because the entire shay had suddenly disintegrated. And that's what we're asking. You live healthily and then suddenly go into rapid decline with this compression of morbidity. And let me point out that so in the UK, if you look over the last many decades, there's been no lifespan has increased, but so has health span, but not sometimes not even keeping up. So that the fraction of our lives that we spend on unhealthy has not actually gone up. Okay. And we heard about this before. So I mentioned in the UK, the number of years spent with 4 or more morbidities has actually increased as a fraction of our lives. And the same is true about the UN World Report. I think somebody showed that in one of the introductory talks. And so the question is, we're spending more years and possibly a greater fraction of our lives in poor health. And so the question is compression of morbidity even possible? Well, there is one interesting finding, and that is studies on supercentenarians shows that they live extraordinarily healthy lives. Many of them have never seen a doctor until they were over 100. And then suddenly they go into rapid decline and die. Supercentenarians are people who live 110. There are not very many of them. Now, the question is whether this can be, they have some general information for the rest of the population. There are 1 or 2 genes that seem to show up above signal, but really, most of them have different combinations of genes. And the fact is, a Danish study showed that lifespan is only about 25% heritable. And so the reality is they've had a combination of life history and pure luck, as well as some genetic heritage that has allowed them to live this long. It may not be translatable necessarily to the general population, and we may be looking at survivor bias. There was an article in a research article just last year suggesting just that. Now, but the question is, can health span be improved? Well, here is the situation in the UK. You can see that you have this is only years above 65, okay? No, this is not from birth. This is a number of years above 65. How much of it do you spend in good health, and how much of do you spend in bad health? Bad health is at the top. And what you notice is in Sweden, they've managed to have a much shorter period of bad health, even though the overall longevity is about the same. The lifespan is about the same. More of it is spent in good health. And I should point out, look at the number for women, which is shown in the reddish or pinkish color. Women, at least in Sweden, have at least as good, or if not better, health span than men do. And this was all done by reducing socioeconomic inequalities and improving population health. There was no sort of longevity therapeutics involved. And so the question is, can other countries do things like that to improve health span? And I think, yes, probably there are a lot of social and public health interventions that we could do to improve health span. But in terms of improving aging itself, if you tackle aging itself, it is not at all clear. There's no evidence that improvement in aging will also not extend improvement in lifespan itself, with the result that the morbidity period will not actually decline with time. And so that is going to be an issue. And one caveat about health span is mortality is very easy to define. It's when a person dies, but it's not so easy to define in terms of morbidity. For example, what does 3 or 4 comorbidities mean? I've got comorbidities. I'm pre-diabetic, I have high blood pressure, I have high cholesterol, and I'm living fine with them. I bicycle and I go hiking and so on. And so the question is, what we really need to measure is healthy life, and that is much harder to measure than a bunch of tests for various comorbidities. And you should also then think about what these statistics mean. One of the final things I want to talk about is economic disparity. In the UK, which has a National Health Service, the disparity between the top 10% economically and the bottom 10% is about 10 years of life expectancy. And in the US, not surprisingly, it's 15 years. Now, the difference in healthy years is almost double. So instead of 10 years, more like 20, or 15 becomes more like 30. It means the poor are living shorter years and spending more of it in poor health. And by the way, I know some of you are from New York City. The difference between the poorest zip code and the richest zip code in New York City is 35 years in life expectancy. And of course, not all of that is longevity. A lot of it is due to crime, drug, poor medical care, et cetera. But there is a big longevity component to it also. And the best way to live long, of course, then means is to be rich, okay? But that's not an ideal solution. And so then the final thing is, should we all live longer lives? I mean, what if we make all these aging interventions and, all these things do is delay the time when we have morbidities, and we're just postponing the period when we're going into decline. It's not that we're shortening it. And so, there is a question of intergenerational fairness. As we get older, we accumulate power, influence, and wealth. If we live longer, and because we're rich, we're going to live longer, we're going to pass on that wealth to our children. They're going to live longer, and you're going to get a two-tiered society. And so so you're going to get increased disparity, and so that's going to be an issue. And so unless anti-aging therapeutics is widely available and cheap, then it's going to increase disparity. Now, some therapeutics like statins or blood pressure medication are widely distributed throughout poor and rich countries, but not organ transplants, for example. Those are very expensive. So it depends on what is the therapy you're going to come up with. And then we talked a lot about creativity, but I want to point out we suffer cognitive decline from the age of 20. It is true that we can maintain competence well into old age, and this is because there are two kinds of intelligence. Fluid intelligence, which is the ability to learn new things, to absorb new ideas, to think fast, etc., versus crystallized intelligence, which is the accumulation of knowledge. Vocabulary, for example, lasts quite a long time. And so if you look at major advances in almost every field, including literature, oddly enough, people are have done some of their best work when they're young. And so we will have an issue. And so the intergenerational fairness, creativity, and the general renewal, new ideas, even social revolutions like racial equality, gender equality. These were mostly driven by young people who were not willing to accept the status quo. So we have to ask, what will a society where you have very slow turnover and people live very long look like? Okay, and do we really want that? And of course, the problem is, if anybody came to you and said, here's a pill that's going to give you 10 years of extra healthy life, it's all been randomized clinically trials, it's FDA approved, et cetera, most of us would take it, okay? Because we all want to live longer. We don't want to die. That's why I'm taking statins and blood pressure medicines. They're essentially anti-aging therapies. So, but there's a conflict between what's good for society and what's good for the individual. And meanwhile, I should say, the trio of sleep, diet, and exercise, which is very old advice, except now we have some understanding of the molecular biology and cell biology for why they work. That combination, which by the way is also synergistic, each one affects the other, is probably better right now than anything available on the market. And then along with that, there are some very trivial things anyone reaching middle age should do, which is get your blood pressure, cholesterol, and diabetes checked because they're easy to test and easy to treat. And some interesting social experiments have shown that social isolation and having a sense of purpose, social isolation is bad for you, and maintaining a sense of purpose in life is good for you. So being part of the community and having a sense of purpose as you get older is really beneficial to your health and longevity. Thank you very much.